So what is dimensionality reduction? So we talked earlier about feature selection, where we select fewer features than the overall features available in the data set. In order to do this, you like to sit here? Yeah, so or I go one step back if you like. You have more places. Okay, so we talked about feature selection, where you select fewer features available at your site than the overall features. And we said there are different approaches, right? We can go with filter approach, embedded approach, and what is the third one? Wrapper approach. Now we talk about dimensionality reduction. Dimensionality reduction is similar in the general concept, where you try to reduce the number of features available, right? So dimensions here, we are referring to the features available at your site. So dimensionality reduction, you're trying to reduce the features available at your site, but using different technique. So earlier in feature selection, we were just simply selecting some, removing others using some technique. But here in dimensionality reduction actually is not necessary, it's just a matter of selection, but probably by generating new features and dropping the existing one. So we'll see how. So dimensionality reduction refers to the process of reducing number of input variables or feature in a data set while preserving the key information pattern. This is important, okay? While preserving the key information or patterns, right? Dimensionality reduction algorithm generates new components. You can think of components as variables, okay? But we refer to them as component because they're gonna actually compose or combine several, can be as a result of all the features you have. We're gonna find out soon when we talk about example of PCA. Let me just remove this. I think I can just use this. Okay. So generate a new component. These new components, as I said, you can think of them as feature. Okay. They should preserve the key information from the original features you have inside your data set. Okay, that are combinations of original features. These new features are often referred to as principal components or latent variables. They call them latent variables or principal components. Okay. One of the algorithms that can be or famous in applying dimensionality reduction, called principal component analysis, or PCA, is known as PCA. So principal component analysis is widely used technique for dimensionality reduction and feature extraction. In data analysis and machine learning, the goal of PCA is to transform high dimensional data set to lower dimensional space, meaning reducing the number of attributes available. But as I said, by generating new components that preserve the key information from the original input, okay, while retaining as much or preserving as much of the information in the original data set as possible. PCA works by identifying the principal components, okay, of the data, which are the direction of maximum variation in the data. These principal components are orthogonal to each other and are ranked in order of their explained variance. Now we see what we mean with the first component explaining the most variance. Okay, so keep this in mind when you generate your components by applying, let's say, PCA. Okay, so as we said, these will gonna generate components. So we can call it PC1, maybe principal component 1, PC1, PC2, and so on. All right. Now, are these just exact features we have? No. Okay, these are extraction of the key information from all features. So what we mean by they are listed in rank in order for their explained variance, meaning PC1 is going to have the highest explanation for the feature. Okay, so it's going to have the highest explained variance for the feature. It's going to contain. In other words, in simple format, it's going to return most of the information from all features in PC1. Maybe PC1 includes maybe, let's say, 80% of the key information from overall features. Okay, you patterns from, or information, key information from the original features, and include them in a new, what we call components. So component 1 or PC1 is going to contain 80% of the key information from the overall features that have been included, while PC2 probably, let's say 5%, and so on and so forth. So the concept is quite different. It's not like feature selection. Just simply say, okay, I take feature 1, 2, 3. I drop 4 and 5. No. Probably you take all 1 to 5, and then you request from PCA to find the key information, or what we call it, the variance inside the data, and then present or preserve this information inside new latent variables, what we call it, latent variables or principal components. So PC1 is going to contain the highest information from the overall data. PC2 probably 5%, and so on and so forth. Okay, clear? Yeah, so it's not just a matter of selection. So in this case, unlike feature selection, the simple feature selection, can we say, let's say if I have a data set where this is, we have age, let's say, for example, years of experience, and what else could be? Salary, whatever. Now in feature selection, simply we may say we are interested in 1 and 2 and removing 3, right? This is simple feature selection. But in PCA, no. We probably take all these features, pass them to PCA, principal component analysis, and PCA is going to generate, let's say we request from PCA, we need only 2 latent variables. So this is going to generate PC1 and PC2. Now, can you say PC1 is representing age? No, because this is like the extraction for key information coming from all features. So we cannot tell what is PC1. If I ask you what is PC1, we don't know, right? You cannot tell me PC1 is age, or maybe combination age and years of experience. We don't know, okay? So simply PCA is going to look for the variance, the key information inside the original features, and generate a new component while preserving this variance or this information. So eventually we cannot explain what is PC1, what is PC2. Okay, we cannot interpret. It's not easy. Okay, for an example here, I included a link for this website. It's quite interesting. They explain the case, and then they provide an example. So this example is taken from their website. Not sure if I can click here. Okay, so actually it's similar to what we have discussed. Okay, so principal component analysis is technique to emphasize on the variation inside the data, the information. Another word, like in simple term, information. Okay, information inside the data, then, and bring out strong patterns from the data set. It's often used to make data easy to explore and visualize. If you want to, like you are extracting what they call, like the nectar, let's say, from flowers, like you're taking the variance or the all information reserved inside the data and present them inside fewer features. So that can help you to visualize and find out some patterns from your data. Okay. So here is giving you an example. Let's consider a data set in only 2 dimensions. Dimensions means feature, such as height and weight. We have only height and weight. This data can be plotted as points in a plane. But if you want to tease out variation, PCA finds a new coordinate system in which every point has a new X and Y value. Okay? These axes do not actually mean anything physically. As I said, we cannot explain what is PC1. Right? Just now what we mentioned earlier, PC1, we don't know. So you cannot explain. So earlier we had height and weight, but now the new generated components, we cannot tell what they are. Okay? They don't actually mean anything physical. They're a combination of height and weight called principal components or latent variables that are chosen to give one axis lots of variation. Okay, so here, let's say you have X and Y. And then in this example, if you click, I remember there was a button to click. Anyway, so as you see here, this is X and Y. Here we got PC1, PC2, right? Different. PC1, PC2. You cannot tell PC1 is X or let's say width and height. This is width and height, okay? Height and width. This is PC1. So as we said, we cannot tell because it doesn't mean anything physical, what is PC1, PC2. But this shows you how it has made the variation of the data, I mean, orthogonal to each other. This is what the slide was trying to explain to you earlier, if you refer back, okay? So now here they're showing you the variation. So PCA is useful for eliminating dimension. Below we plotted the data along a pair of lines, one composed of X values, another of Y value. If you are going only to see the data along one dimension, though, it might be better to make that dimension the principal component with most variation. We don't lose much by dropping PC2. So this is what we said earlier. PC1, they're going to be in ranking. PC1 is going to retain most of the information from X and Y in this example, while PC2 is going to be very less. So actually, if you observe that, PC1 has most of the variation, right? So the variation, you will see that PC1 value varies a lot between -3 plus -4, right? Well, if you investigate PC2, mainly or around 0. So they explain nothing. They don't provide any information. So in this case, if you drop PC2, would be fine because actually it doesn't give you much information, no variation, no information much retained in PC2. Okay, does that mean PC1 include all the information? No, you already have lost some of the information, but majority have been retained in PC1. Okay, this is for 3D example, similar. So where you have with 3D, PCA is more useful because it's hard to see through a cloud of data. In the example below, the original data are plotted in 3D, but you can project the data into 2D through transformation. No different than finding a camera angle. Rotate the axis to find the best, blah, 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 and so on. Okay. So here, after you apply PCA, notice how PC1 will include most of the variation inside the data, while PC2 and PC3, they have very low variation, okay? So majority of the data, the key information are preserved in PC1. This is our example, the one inside the slides, okay? So eating in the UK. So we are interested to find out the general behavior of people eating in UK. Okay, so what if our data have more than 3 dimensions? So here you are given an example where your data has many dimensions. How many dimensions we have here? How many dimensions? 4 or 17? Okay, look for, yeah. So it's 17 dimensional. You need to understand the objective. And here it's confused because the data looks, the column actually are the rows and the rows are the column. You need to rotate the figure, right? So here we have the features because we're looking for eating habit, right? So eating habit, if I ask you eating habit, how you can, what type of feature you want in order to find patterns inside for eating habit? You want country or you want the list of food items, the consumption of items in order to find behavior? These are just examples. These here are examples. Records. Maybe Malaysia can be one of them and so on and so forth. Just examples, right? But the actual features, the attributes are these, because after all, these are linked to eating or looking for eating, right? So not countries, right? So we have here 17 features. And let's say we are interested to find probably general pattern from these 17 features for 4 countries. So here we have only records for 4 countries. Like the example in practical, we have 4 districts, for example, okay? Well, among those, we have features. In this table is the average consumption of 17 types of food in gram per person per week for every country in UK. Okay, so this table showing you, again, the average consumption of all these 17 types of food in grams per person per week for every country. Okay. The table shows some interesting variation. So if you look here, there are some different variation between the consumption of each country, or maybe less, here more, maybe those all has high consumption, right? And so on and so forth. And but overall difference are not notable. So if you like to have insight about their overall eating behavior for the 4 countries based on the 17 features, you cannot tell. You cannot tell just for the overall. You can't tell maybe for specific. Maybe you tell me, okay, regarding beverage, maybe we notice 3 countries are almost same, while the last one, let's say, is different, right? So if I'm asking you to describe the consumption behavior for specific feature, then that's fine, correct? But if I ask you all combined together, give me the overall difference, then it's quite difficult. You cannot tell, right? It's impossible. And even visualizing them all together, also difficult. 17D is impossible to visualize, right? So what we need to do in this case, can we apply feature selection, simple feature selection? If we apply, then what's going to be like the solution you are going to build? If we apply simple feature selection, I'm not talking about PCA, simple feature selection, meaning in this case, maybe you say, okay, I'm going to study only the overall behavior for these 4 countries for only maybe cheese, confectionery, fat, and oil. Maybe because you can only draw 3D most, correct? This is a simple feature selection. But I'm asking you for overall, all together combined. Then simple feature selection may not be suitable for this case. If you are looking for all combined 17 types of food, right? We cannot draw, we cannot visualize, and it's quite difficult to come up with overall statement about their behavior consumption for the 17 types of food. And if we go with simple feature selection, only we can pick 2 or 3 because we can visualize, fine, up to 3 probably, but more than that becomes difficult. So this won't help us to find out the overall for the 17 types of food. So what we do in this case, we need PCA. Because why? PCA can help us, 1, to reduce, right? Reduce dimensions or features. But this is still same like simple feature selection. Second is most important. What is second? What is second? Preserving the key information from all combined 17 features into fewer number of features. Well, the first feature or latent variable given by PCA is going to actually even reserve the highest number of variation. Most of the variation is going to be inside PC1. So probably if I take PC1, PC2, PC3, or only PC1, PC2 can be enough because knowing PC1 is going to contain maybe 80% of the variation. PC2 probably 5%. So I have 85% of the variation had been extracted and combined all inside only 2 components, which is quite good. So now I can visualize 2 components later, right? So the second one is preserving or retaining most of key information from the 17 types of food into, right, fewer, probably just 2D dimensions, right? Dimensions, right? Which is quite good. Once I have, let's say 85% or 90% of the variation or the key information from the original data into only 2 components, then I can visualize 2D and I can immediately get some insight. You got the point? So simple feature selection won't be working for this example. but we need PCA because PCA has number 2, which simple feature doesn't have, cannot produce. Okay, clear? So both of them share the same topic, the same concept as a general reduced dimension, but PCA is more powerful because it can retain the key information from all features into fewer number of what we call latent variables or principal components. Clear? So let's look into one dimension. You see, let's say we applied principal component, you see, into one. So this is only PC1. So what you can observe immediately, just looking into this figure, what can you observe? Yeah, which is PC1, correct? But what can we observe about the eating behavior of these 4 countries, Wales, England, Scotland, and North Ireland? Just anything can drag your attention. I'm sure something distinct, these 4 among each other. What is it? Quite clear, North Ireland, quite different from the others, right? Wales, England, and Scotland are almost near to each other, correct? While North Ireland is quite different. Immediately, just you see, just apply PCA, we got some insight. North Ireland is a quite different country in terms of eating consumption than the other 3 countries. Okay? Okay. So as we said, since PC1 will contain most of the information, so we can see something different about North Ireland, right? Now let's see first and second principal component. How about first and second principal component? Same thing. Still North Ireland looks different, or even we can consider it as outlier because it's quite different than the other 3 countries, right? So once we go back and look at the data in the table, so now once you have this insight, probably you can refer back to your table to find out what's different about North Ireland, since now you have some information. Okay, so this makes sense. The North Ireland eat way more grams of fresh potato and way fewer of fresh foods. Okay, cheese and fish and other alcoholic drinks. It's a good sign that structure we visualize reflect a big fact of real-world geography about North Ireland is the only of the 4 countries not on the island of Great Britain. Okay, so here it's more about geography. Clear? So how PCA has helped us to figure out some overall, what is the overall difference among the 4 countries? Okay, so if you want to subscribe, put your email. Okay, so this is the same what now just we discussed. Okay, so overall, the course of dimensionality is a phenomena that occurs when working with high dimensional data, where number of dimension features in the data is much larger than the number of samples. This is maybe as something you can look into as a rule of thumb. So if you have larger number of features according to the number of samples, like the example we had 17 features versus only 4 samples, right? So in this scenario, the data becomes increasingly sparse and uniform in the high dimension space, making it difficult to distinguish meaningful patterns or relationship. Okay, so overall, if you have many problems arise in high dimension space, so you may look to PCA, okay, as because high dimensional vectors are generally very sparse. Sparse meaning, again, zeros, right? Sparse referring to a lot of fields where the information probably is just 0. So you cannot, extracting patterns become very challenging, okay, when you have sparse data, okay? And increase the risk of overfitting. So since you have probably complex data with a fewer sample, because fewer sample indicate the algorithm, whatever you have included, is very difficult to extract patterns when you have high number of dimension with fewer samples or records. Okay, is it clear? So as a conclusion, again, summary, for the motivation behind dimensionality reduction can be to speed up the speed of subsequent training. So if PCA is part of your pre-processing, so that means training later during modeling time is going to be faster since you have fewer information, correct? To visualize the data to gain insight, like the example of UK. Just now, we've seen an example of UK, how we were able to gain insight from the data. As having high dimension data is difficult to visualize, so we reduce the number of features into fewer features, again, while retaining key information. Okay, this is quite important. Reduce the noise can be also helpful. In some cases, it might be even remove noise and redundant feature, making training algorithm. But again, some cases, sometimes keep in mind, when you are working on machine learning, it's about trial and error. So you need to try and find out whether it's working or not. Now, enhance interpretability, simplify the dataset, making it easier to understand and interpret the relationship between the variables. Actually, this one, I think it's not quite straightforward, this part. Okay. If you are about interpreting instead of variables, probably the samples in general, or maybe based on the insight like the UK example, then you need to refer back to your original data set, then fine. If you think of it from that perspective, then fine. But only looking into PCS, meaning principal components, cannot. Okay, by only looking. Because eventually you are looking to interpret relationship between variables. Okay. Finally, to save space. So if you have a huge amount of data, so PCA can help you eventually to reduce the size of your data. And another matter actually is quite interesting. You see some people using PCA for what? Anyone can tell? Did you study which course? Professional ethics? Professional ethics. On the way. Okay. For those who studied, what is the matter if you have data? What is the big issue when you have data collected from people? For those who studied, yeah, and the privacy of the data. So exposing the data to the public can put you in legal action, right? I mean, people can take action against you. So how to make the data anonymous? PCA can help you as well. So if you want to disguise the original data, because PC1, PC2, PC3 has no meaning. So we don't know what is PC1. Is it age? Is it type of relationship? Number of kids? We don't know. So PC1, PC2, PC3 has become like encrypted data. We don't know what is this data, right? So I saw some people would do this in order to disguise the original data and just provide you the output of PCA to you, okay? To do machine learning, let's say for eating behavior. So instead of providing maybe these countries with the name of the features, just I give you PC1, PC2, PC3, PC4. And then you need to go ahead with the 4 countries and just find out what's about it. But what's about Ireland in particular, we don't know, okay? What is the drawback behind dimensionality reduction? Meaning what can cause someone not to consider? Some information eventually are lost. As we said, it will retain most of the key information, but not all the information, okay? So it's possibly degrading the performance of next algorithm. So probably the performance of your algorithm might drop down because you're not having all the key information, okay? Computationally intensive because that required additional process during data pre-processing, right? You need to apply PCA during data pre-processing, so that can make computation more intensive and add, of course, complexity to the pipeline. So maybe these are linked to each other. So eventually you are adding more process into the pipeline, make it more complex. And transformed features are often hard to interpret. As we said, what is PC1? We don't know. PC2, we don't know. Okay, so it's hard to interpret what these new components are. Okay. So as a conclusion, should you consider PCA or not? It's best to try training your model with the original data first, without PCA, before deciding to use dimensionality reduction. Although there are situations where reducing dimensionality of the training data may help improve the performance by filtering out an unnecessary detail. Just now, as we mentioned earlier, can reduce the noise inside your data in some cases, can reduce the noise and redundant data. However, in most cases, it will only speed up the training process and not result in better performance. Okay, as overall, it may not actually, most of the cases, most of the time, may not improve your performance. Just it will speed up the training process. Okay. How to apply all this? We spent, I don't know how long we're talking. Just, you see, 3 lines. Import, create an object, and here where you need to define the number of components. So you need to select whether, let's say from like the example we had earlier, 17 features for UK, whether you need to come up, reduce them to 2. So by specifying the number of components. If you say 2, this will give you only 2 components, PC1, PC2. Okay? And then you call fit and transform. That's it. Okay?